Let us start with sequences again. In the last lecture we have seen certain algebraic properties of the sequence. That is, let us say I have a sequence xn and I have a sequence yn such that both the sequences are convergent and xn converges to L, yn converges to M. Then we have that xn plus yn converges to L plus M. Similarly, we have certain result about multiplication of sequences also. That is, given the sequences xn and yn, I can look at a new sequence zn. This is defined by xn into yn for all n, and then we have seen that it implies zn also converges and it converges to Lm. Similarly, we have something about xn divided by yn, of course under the condition that yn is bigger than 0. This implies that this new sequence, which I might call wn, this wn then converges to L by M. Now the importance of these results actually is that given limits of sequences, we can certainly find out limits of some other sequences made out of the old sequences. For example, let us look at the sequence xn, which is given by 2n by 1 plus n square, where n is bigger than or equal to 1. Now we want to know what is the limit of this sequence, if at all it converges. We will see very soon that it does. Well, what we do is we write xn as 2 divided by n square divided by 1 by n plus 1. That means I am just dividing the numerator and the denominator by n square. Now let us concentrate on the numerator, which I can think of it as x prime of n, which is 2 by n square. What is the limit of this sequence? Well, by Archimedean property I have that xn prime actually converges to 0. Well, what about 1 by n plus 1? I call this sequence xn double prime, which is 1 plus 1 by n. Notice that I already know that 1 by n converges to 0. Then think of this 1 as the constant sequence 1. That is, it is given by Zn equal to 1 for all n. And then we know that the sequence Zn converges to 1. This implies that the sequence xn double prime, using our previous result, that it converges to 1 plus 0, which is equals to 1. Well, now then I have that xn equals to xn prime divided by xn double prime. And I know that xn double prime converges to 0. Well, sorry, xn double prime converges to 1 and xn prime converges to 0. Then again use a previous result. This implies that xn converges to 0 into 1, which is 0. Well, this is how, given old sequences, we can produce new sequences which converge, and we can find out our limit in terms of the old sequences. But now the important question arises that after all, when does a sequence converge? Is it necessary that if I want to find out whether a sequence converges or not, is it really necessary to know what exactly is the limit? That is the question we are going to address. But first, we would like to have a necessary condition under which a sequence converges. Well, let us first observe one thing. I will call it a proposition, which is really easy to prove, follows straightway from the definition. If a sequence xn converges, then the sequence is bounded. Well, what does a bounded sequence means? A bounded sequence means it's a sequence xn such that there exists a real number m with mod of xn is less or equals to m. That essentially means the whole sequence can be thought of as a subset of the interval minus m. Okay. Well, let us see how does the proof follow. Since I said the sequence xn converges, that means there exists a real number L where the sequence converge. So, there exists L, a real number, such that xn converges to L. Well, then I apply the definition. I take epsilon equal to 1. Then there exists a stage such that after this stage the whole sequence xn actually is in the interval L minus 1, L plus 1. This implies that mod of xn minus L is less 1, which again implies mod of xn lesser equals to 1. Okay. But this happens after certain stage. If I have to prove that the sequence is bounded, I have to show that there exists a number m such that all the terms of the sequence are less than that number m. Well, I have shown it that this is true after certain stage. Well, what happens to the previous stages? Notice that there are only finitely many stages, x1, then x2, it remains up to xn minus 1. And after this, whatever xn I have, they satisfy the inequality, that this is lesser equal to 1 plus L. Then to arrange the bound which I called m, what I do is I just look at the maximum of the numbers x1, x2, xn minus 1, and then I look at 1 plus mod L. This certainly exists, which I call m. Then this implies that mod of xn, well, let me put mods here also. Then it implies that this is lesser equals to m for all n. This implies the sequence is bounded. Then the question remains, is the converse true? So, the question is every bounded sequence well, the answer is no, and we can easily see that if I look at the sequence xn equals to minus 1 to the power n, then it is clear that mod of xn is lesser equals to 1 for all n. But we know that the sequence does not converge, but xn does not converge. So, the question then remains, and that is the most fundamental question which we are going to take up now, that bounded plus what extra condition I need which will imply convergence. Well, I will try to supply one such condition first. So, let us see one such theorem in this direction. For that, first I need one definition. So, the definition what I need is of a monotone sequence. So, what is a monotone sequence? Well, a sequence xn is called monotone increasing, in short mi, if xn is less or equal to xn plus 1 for all n. That means as you go towards infinity, your terms are slowly increasing one after other. Similarly, the reverse of this is called the monotone decreasing sequences. That is, if xn plus 1 is less or equals to xn for all n. And the sequence is called monotone if it is either monotone increasing or monotone decreasing. So, a sequence is called monotone if it is either monotone increasing or monotone decreasing. And we will try to prove that given any sequence, if it is bounded and it is monotone, then it actually converges. And we have seen some such examples. For example, if I look at this sequence, xn equals to 1 by n for all n. We have already seen that the limit of this sequence is 0. Well, notice that this sequence is a bounded sequence. It is anyway bounded by 1 and in the below it is bounded by 0. And certainly it is monotone because as you go on increasing these n's, the numbers actually decrease. So, it is a monotone decreasing sequence. Similarly, I can look at xn equals to 1 minus 1 by n. Since I know that the sequence 1 by n converges to 0, that means 1 minus 1 by n, that converges to 1. And this sequence anyway is monotone increasing because as you go on increasing the n's, this 1 by n's are decreasing. That means 1 minus 1 by n's are increasing. And there is nothing holy about this 1. In fact, I can look at xn prime equals to minus 1 by n. Then this sequence also converges to 0 and it is now monotone increasing. So, let us try to prove the theorem now. If a sequence xn is bounded and monotone increasing, then xn converges. Well, I have stated the theorem just for monotone increasing sequence, but you can prove the same result for monotone decreasing sequences also. Just look at the proof which I give you, then try to mimic the proof. The result will follow analogously. And the proof essentially is just drawing the picture. It will follow that way. So, before writing down the formal proof, let me just draw the picture of this. So, this is real line and the sequence xn points are here, but there is a bound here, let us say m, and there is a minus m here. Okay. Now, the sequence has to converge somewhere. Well, first you have to somehow get hold of the candidate who can be the limit of the sequence. Who can be the candidate first of all? Well, once somebody gives you a bounded non-empty subset of real line, then the first thing you will think about is its supremum. Well, you can think about its infimum also. Let us get hold of the supremum first. So, supremum of the xn's let us look at, and let me call it L. Since I am always denoting the limits by L, now you can guess that this L is actually going to be the limit. Let us try to see whether it is true or not. So, I take any epsilon bigger than 0. That means I have L here and I am choosing an interval around this. Well, now the first thing I know is that this L minus epsilon, this certainly cannot be an upper bound of this xn's, because if it is, then this L cannot be the supremum, right, because L minus epsilon is less than L. Means what? It means there exists a member of the sequence which surpasses this L minus epsilon, that is, it is sitting somewhere here. At the same time, you notice that all these xn's are actually less than L and it is monotone increasing. So, what happens to L xn plus 1? If I want to look at xn plus 1, it has to be somewhere here. Then xn plus 2 is sitting here, so is xn plus 3. That means after this xn, all the terms are actually between L minus epsilon and L by monotonicity of the sequence. Well, that is the proof. So, let us just try to write it down formally. Let L supremum of xn. in the bracket I will write L exists as xn is given to be bounded. Choose epsilon bigger than 0, then by definition of supremum there exists capital Xn such that capital Xn belongs to L minus epsilon, L plus epsilon. The rest is simple. Since Xn is monotone increasing, Xn is lesser equals to Xn and Xn belongs to L minus epsilon, L plus epsilon for all n bigger than or equals to n. But isn't this the condition which you want for the convergence of a sequence? Well, this completes the proof. If you want to prove an analog of the same result with monotone decreasing sequence, then what is the change? The only change is instead of this, the supremum, rather we should look at the infimum. Then the rest of the proof is exactly same. Now the next question we are going to address is, can we really talk about convergence of a sequence without referring to its limit? Because as it happens that given a sequence, it might be extremely difficult to find out exactly what the limit of the sequence is. So without referring to the limit, can I talk about convergence of a sequence? Well, if you look back at the definition of the convergence, it actually involves the limit. So is there any way to define convergence without referring to the limit? Well, that brings us to the notion of something called Cauchy sequences. That is the thing we are going to take up now. Cauchy sequence. It comes out from a very intuitive way of looking at the convergence, that Xn converges to L implies after some stage all the Xn's are very close to L. Now from this statement, if I want to get rid of this L, can I think of it this way, that all the terms of the sequences are getting very close to each other? So is it same as saying that after some stage all terms of the sequence Xn are close to each other? We want to see whether it's true or false. I would say intuitively it looks correct to me, because if all the terms after certain stage are getting close to L, certainly they are getting very close to each other. But still some amount of quantification is actually required, follows from this example. Let us look at the sequence Xn, which is given by square root of n plus 1 minus square root of n. Well, sorry, let me look at this sequence. Xn equals to square root of n, certainly a divergent sequence. But notice that if I look at xn plus 1 minus xn, which is square root of n plus 1 minus square root of n, which can also be written as the product of correct This is very simple. Now if you compute the numerator, it comes out that this is equals to 1 by square root of n plus 1 plus square root of n. What does this show? Well, it shows that this goes to 0 because the denominator converges to infinity, and I am looking at something like 1 by infinity, so that goes to 0. It implies that although xn plus 1 and xn are close to each other, after some stage xn is not convergent. That means just two consecutive terms as you go towards infinity, they are getting close. That does not ensure the convergence of the sequence. What actually you need is all the terms after certain stage, they can be squeezed together almost. That is the meaning of the, that will turn out to be the meaning of the convergence. So let's try to proceed in that direction. So first I define something called Cauchy sequence. We will see that the definition actually contrasts with the previous example in certain way. I say a sequence xn is called Cauchy if given epsilon bigger than 0, there exists a stage such that after this stage, if I take two elements, then the difference between xm and xn is less than epsilon. Well, here one thing I haven't written, but you should understand that I actually mean, that means whatever short length you assume, after certain stage, any two elements, they have the distance less than that epsilon. Well, with this epsilon, this n will vary. That is the only thing. So I can actually write n epsilon. Notice that if I have this sequence, xn equals to 1 by n, I say xn is a Cauchy sequence. How does this follow? I pick any epsilon bigger than 0. I have to find a stage capital N such that n m bigger than capital M implies mod of 1 by n minus 1 by m is less epsilon. This is my job. Well, to make this less than epsilon, I say it is enough to show that 1 by m plus 1 by n is less epsilon. This implies then, if I assume that m is bigger than n, that 2 by n is less than epsilon. But I can always find some such n, again by Archimedean property. There exists capital N such that 2 by capital N is less than epsilon, and that finishes the job. And I already know that the sequence xn actually converges. So it might happen that if a sequence is Cauchy, it does converge. Well, to prove that, we have to prove certain things first. The first thing I need is first an observation. Let us write it this way: proposition. Let xn be a convergent sequence such that xn is less or equal to m for all n. I say this implies L is also less or equals to m. You can take it as a little exercise that if mod of xn is strictly less than m, does this imply L is also strictly less than m? Think about it. Now, how to prove this? Proof is again simple. Assume that L strictly bigger than m. Then anyway we can manufacture epsilon such that L minus epsilon is strictly bigger than m. Okay. And then I look at now I know since the sequence xn converges to L, after certain stage all the xn's are inside L minus epsilon, L plus epsilon. But that implies those elements xn's are actually bigger than m, which they are not allowed to be. I say by definition of convergence this implies that xn belongs to L minus epsilon, L plus epsilon for all n bigger than or equal to some capital N. But this implies xn is bigger than m for all n bigger than or equals to n, which is a contradiction. Correct? Because all the xn's are supposed to be less than m. The next thing I need, this is called the Cantor intersection theorem or the nested interval theorem. It is again another statement which seems intuitively very clear, but surprisingly it requires a proof. Well, the theorem is that suppose In is a closed interval given by An and Bn for all n, such that In plus 1 is contained in In. That means as n increases, the intervals are getting smaller and smaller. One is contained in the other, and that is the meaning of the word nested. Okay. Also assume that the closed intervals a and bn's are getting smaller and smaller. That means the intervals are actually squeezing. That means their lengths are actually going to 0. So that is the next statement. If bn minus an, notice that this is nothing but the length of the intervals in. Okay, if this goes to 0 as n goes to infinity, then what happens to the total intersection of the i's? Does it become an empty set suddenly? The answer is no. It is still non-empty, but there is only one point in the intersection. Then intersection over n in contains a single point. Okay, so let's try to prove this. First, let's consider the sequence an. This is the left end points of in. Similarly, I can consider bn's also, that is the right endpoints of in. So somehow I have manufactured two sequences and I want to talk about its limits. Well, the question is, are these sequences convergent? I say yes, because as in's are getting smaller and smaller, this is my I1, so A1, B1, then I look at I2, which is A2, B2, then I look at I3, which is A3, B3. It follows that the sequence an is an increasing sequence. It follows that an is monotone increasing and the sequence Bn is monotone decreasing. Now if I want to ensure that the sequence ANs converge, what else I need? Every monotone increasing sequence doesn't converge, right? You can look at the sequence xn equals to n, it goes to infinity. So the condition you need is bounded, that I have proved few minutes back. Well, let us see whether the sequence AN is bounded. Notice that all the ANs which I am looking at, they are actually bounded by B1 anyway. As AN is lesser equals to B1 follows straight away from the picture which I have drawn for all n, and the sequence Bn's, it is actually bounded below by A1 for all n. We have that both the sequences converge. Okay. Now I need to know what is the relation between A and B, right? Now I apply the previous result which I have proved. All the ANs are lesser equals to, since ANs, now notice that AN is lesser equals to BM for all n and m. That again follows from the picture. Okay. This implies then, by our previous result, that A is lesser equals to Bm for all m. Then again, reapplying the lemma, it follows that A is lesser equals to B. Okay. If I can somehow show that A is equal to B, then I am through, right? Now here actually the role is played by that the distances are actually going to 0. So let us try to see why. Now to see this is very easy. Just notice one thing, that B minus A is certainly less or equals to Bn minus An for all n, correct? And I also know that this is bigger than or equal to 0, that I have proved. But as n goes to infinity, this converges to 0. This I treat as the constant sequence which converges to 0, and then I use sandwich theorem. That means this converges to 0. But this converges to 0 means what? It is the constant sequence. This implies A must be equal to B, and that is it. That is actually in the total intersection. But it still remains to prove. All I have proved is there is something in the total intersection. Well, there might be some other C in the total intersection. Why there is only a single point? Suppose there is some other element C in the total intersection. So assume C, which is not equal to A, is in intersection IN. Means what? It implies that the set A and C, it is actually contained in IN for all n. This implies that Bn minus An, which is the length of the interval, is certainly bigger than or equal to C minus A for all n. And then the length Bn minus An, which is supposed to go to 0, is not going to 0, which is a contradiction. Means what? It means there is no such C, and anyway there is A. So that means the total intersection must be a singleton. So this completes the proof. An important corollary of this nested interval theorem is the so-called Bolzano-Weierstrass theorem. But before I come into that, let me explain certain notions first. So the notion I need is the notion of subsequence. Well, what is a subsequence? It is something like you have given a sequence xn and you just forget certain terms of it. Whatever remains, don't change the order, look at them exactly in the same order, what you get is a subsequence. So in particular, a sequence is certainly a subsequence of itself. First let us look at examples and then we will give you the definition. Let's look at this sequence xn equals to minus 1 to the power n. And I say this sequence 1, 1, 1, 1 is a subsequence because it is nothing but x2, x4, x6, x8, x2n and so on. You see what I have forgotten? I have just forgotten the odd terms. Similarly, I can look at minus 1, the constant subsequence, which is nothing but x1, x3, x5, x2n plus 1 and so on. Okay? And notice that the sequence xn doesn't converge, but the subsequences which I have picked up, they converge. Okay? That means this sequence has at least got two subsequences which converge. That means even if the sequence is bad, it might have good subsequences. Okay? So what I do is, first I choose a sequence of natural numbers n1 less than n2 less than n3 less than n4 and so on, and then look at the corresponding terms on the given sequence xn, that is xn1, xn2, xn3, xn4 and so on. It just means I have picked up certain terms from the sequence xn without changing their orders, the way they were arranged exactly in the same way, but I have deleted certain terms. What produces is a subsequence. This is a subsequence of xn. Well, what is not a subsequence? For example, let us look at this sequence xn equals to n. So the terms are 1, 2, 3, 4, 5 and so on. If I look at this now, 2, 1, 5, 6, 8, then this is not a subsequence. Why so? Because I have changed the order here, which I am not supposed to do. Okay? And since a subsequence is also a sequence, that means there also has to be infinitely many terms in this. Okay? It cannot certainly stop. That means it is not really just a subset of the sequence. It itself has to be a sequence. Now, I will try to show that what happened with the sequence xn equals to minus 1 to the power n. I could manage to get two subsequences. Remember, one was yn equals to the sequence 1, constant sequence 1, and the sequence zn, which is given by minus 1 to the power n. This minus 1 to the power 1, these two sequences were convergent. Well, we will try to show that this is not really an accident. Given any bounded sequence, we can always do that. At least we can always be able to find a subsequence of the sequence which converges, although the whole sequence may not converge. For example, this minus 1 to the power n, the whole sequence doesn't converge, but I could extract a subsequence yn which was convergent. Well, this is precisely the message from the Bolzano-Weierstrass theorem. So let's now state the theorem. Well, the statement of the theorem says that if xn is a bounded sequence, then it has a convergent subsequence. We will see the proof of this actually follows as a corollary of the nested interval theorem. Instead of writing down the detailed proof of this result, let me try to explain it pictorially, what it means. Let us first draw the interval minus mm within which my sequence lies. Okay, let me first pick x1, then I subdivide this, then either this contains infinitely many elements or this portion contains infinitely many elements. Let us assume this portion contains infinitely many elements. Let me draw it separately here. Okay, and from this I pick xn2. Okay, now what I do is I subdivide this interval. Now again, either this part contains infinitely many elements or this part contains infinitely many elements, since the sequence is infinite. Let us assume that it belongs to this part. Now what I do is I write this separately here, and I write it in a slightly magnified way, okay, because I have to subdivide further. And let me pick xn3 from this part. Well, I will make a choice. The choice is I will always assume that xn2 is with the condition that n2 is bigger than 1, and here I make the choice that n3 is strictly bigger than n2. That choice I can make because I certainly have infinitely many elements at my disposal, so I can anyway choose them. Now again I subdivide this fellow into two parts, two equal parts. Now either this has infinitely many or this has infinitely many. Let's assume this has, then again I will write it here and I will pick an element xn4 from there with the condition that n4 is strictly bigger than n3. Okay. Now from this we can see that we can get a subsequence xnk such that if I call this subinterval I1, this subinterval I2, this I3, this I4, what I get is that xnk belongs to ik. It is also clear just from the construction that it is a nested sequence, that is ik plus 1 is certainly contained in ik. And the way I am doing it, certainly the lengths are increasing, that you can see from here. First length was this portion, then it was this portion, then it was this, then again getting half. So it is going down to 0. That is, length of ik by L of ik, I mean the length, it goes to 0 as k goes to infinity. Now I am in a position to apply the nested interval theorem. That is, I look at intersection of ik. Then by the nested interval theorem, there is some x0 sitting inside this, and I say that this implies that the subsequence xnk converges to x0. Well, this is what we are trying to find out.